Hello everyone, this is Sankurogoy and welcome to this presentation of compressible and incompressible flow of fluid. As we have known, fluid mechanics plays a crucial role in understanding how fluids behaves in motion. And today we will explore the key difference of compressible and incompressible flow, their governing equations, and their main difference and their applications. So let's start our presentation. So first is the introduction of fluid mechanics. So what is fluid mechanics? Basically, the study of fluids in motion is normally called fluid mechanics. And there are types of fluid mechanics: compressible and incompressible flow. Key concepts of these compressible and compressible flows like density, velocity, pressure, and temperature. Coming to the next slide, here we have seen the diagram of compressible and incompressible flows. Simply, in the first diagram, compressible flow which we can compress the flow, and in incompressible flow we cannot compress the fluid. Getting my point? So okay, coming to the next slide. This is the overview of compressible flow. So mainly the flow where the density changes significantly. The flow where the density changes significantly, that type of flow is called compressible flow, like air at high speed or gases under high pressure. Coming to the next slide, incompressible flow where density remains constant. So main difference between compressible and incompressible flow is that the change in density. So where the density remains constant, it is called incompressible flow, and where the fluid density changes significantly, that is called compressible flow. Uh, Incompressible flow, where you can see is the water flow in pipes or low speed airflow. Next is the key difference between the compressible and incompressible flows. So first difference is that is the density, based on their density. Incompressible flow, as we have already studied, incompressible flow, the density varies, but in incompressible flow, the densities remain constant. Second difference is that compressible flow mainly used in high-speed applications, and the incompressible flow mainly used in low-speed applications. So now another difference is that the flow rate. Flow rate is nothing but the multiplication of area and velocity. So in incompressible flow, the flow rate remains constant because the velocities remain constant. And in compressible flow, the flow rate doesn't constant. The inflow and outflow doesn't match with each other. So this is one of the difference between compressible and incompressible flow. Now, another term is Mach number. So Mach number, what is Mach number? So the ratio of flow velocity to the speed of sound is called Mach number. It is nothing but V by A. V is velocity of flow velocity and A is velocity of speed or speed of sound. So based on Mach number, we can differentiate compressible and incompressible flows. So when the Mach number is less than 0.3, then the flow is considered as incompressible flow. And when the Mach number is larger than 0.3, then it is considered as incompressible flow. Oh, sorry, compressible flow. So the main difference is what? If the Mach number is greater than 0.3, then it is considered as compressible flow. And if the Mach number is less than 0.3, then it is considered as incompressible flow. Okay, I think you can getting my point. And the next slide is about the governing equation of compressible and incompressible flow. So there are three types of governing equation. First is based on conservation of mass, then conservation of momentum, and then conservation of energy. So the first is conservation of mass. So conservation of mass contain continuity equations, conservation of momentum contains Navier-Stokes equations, and conservation of energy contains first law of thermodynamics or the energy equations. So the first is continuity equations. So the equation for conservation of mass is specified as d rho bate dt, differentiation of rho bate differentiation of t, d rho bate dt. So the equation for conservation of mass is specified as d rho bate dt plus rho is density multiplied by. So the first equation is continuity equations. The equation of conservation of mass is specified as d rho bate dt plus rho into divergence of velocity, which is equal to 0, where rho is the density and b is the velocity, and divergence is the gradient operator. So the gradient operator is nothing but del bate del x I cap plus del bate del y into j cap plus del bate del z into k cap. For incompressible flow, we already studied that for incompressible flow, the density remains constant. So the continuity equation, it becomes what, d rho bate dt, which is equal to 0. So it becomes the divergence of velocity is du, divergence of velocity will become equal to 0. It means du bate dx plus dv bate dy plus del w. So the now the continuity equations. The equation for conservation of mass is specified as d rho bate dt plus rho into divergence of velocity, which is equal to 0. So here rho is density, fluid density, v is velocity, and this is the gradient operator divergence. So the gradient operator, we can write this as del bate del x into I cap plus del bate del y into j cap plus del bate del z into k cap. For incompressible flow, as we already studied, the density remains constant. It means differentiation of density with respect to time will become 0. So divergence of velocity will also equal to 0. It means del u bate del x plus del v bate del y plus del w bate del z will equal to 0. Next comes to the Navier-Stokes equation, which is based on conservation of momentum. So this equation we can write like del bate del t into density into velocity plus divergence of rho into v square, you can say v square, is equal to negative of divergence of p plus divergence of this tau double bar plus rho into g. So here p is static pressure and tau double dash or double bar is called viscous stress tensor, and rho g is gravitational force per unit volume. So if the fluid is assumed to be incompressible with constant viscosity coefficient mu, then the Navier-Stokes equation simplifies to density multiplied by dv by dt is equal to minus of divergence of p, which is pressure, plus mu into this is divergence square into v plus rho into g. So this is the Navier-Stokes equation for incompressible flow. Now the basic governing equations for compressible flow. So first, we already studied the continuity equations. Then we have Euler's equation, then energy equations, and Navier-Stokes equation. So continuity equation based on mass conservations. Euler equations describe the fluid motion in compressible flow. Then we have energy equations that relates temperature, pressure, and velocity. And Navier-Stokes equations, or as I already shown in the slides, the equation of Navier-Stokes Navier-Stokes equations for incompressible flow. Next, the governing equations for incompressible flow. For continuity equations, same, the mass conservation based on mass conservation, where density is constant. Next, we have Bernoulli equations. So in case of incompressible flow, we have governing equations, we have Bernoulli equations that based on pressure, velocity, and elevations. And we have then we have Navier-Stokes equations for incompressible flow. Then we next come to the next slide. This is shock waves in compressible flow. So in compressible flow, we can see various types of waves. So this is one type of waves which is called shock waves. So what is the main definition of shock waves? So shock wave means sudden changes in fluid properties in supersonic flow. So how it form? So when an object moves faster than the speed of sound, then in that case shock waves form. So what are the characteristics of shock waves? Like sharp increase in pressure, temperature, and density. So in shock waves, so we can see these types of changes. So next, some flow characteristics of incompressible flow. Like in the previous slide, these waves we can see in compressible flow, and in incompressible flow we can see many other changes or many other characteristics like steady flow, streamline, flow pattern, and Bernoulli equations. So as I already mentioned, in incompressible flow the velocity remains constant at every point, so we can say that incompressible flow is a steady flow. Next is streamlines. So streamlines mainly represents the flow directions, and next is flow pattern. So in incompressible flow, so in these types of flow we can see some patterns like laminar and turbulent flow, which will not be seen in compressible flow. Next is Bernoulli equations relates pressure and velocity in steady flow. Okay, now let's come to the application of compressible flow and incompressible flow. First we have compressible flow. So as I already mentioned, compressible flow mainly used in high speed aircrafts and spacecraft. And like there are various types of use we use in industrial applications like gas pipelines or compressor. Because in these types of applications, there is a high speed transmission of flow. So in these cases, so we have to use compressible flow. So here we have two examples. Like in the second diagram we can see the turbine stimulation, and in the first diagram you can see the aerodynamics of an F1 car simply. So next is the application of incompressible flow. So incompressible flow mainly used in applications where the speed of flow is very low, like in hydraulics, flow of water through pipes, pumps. In these cases, incompressible flow is used. And also in flow in rivers, canals, and drainage system, the flow of the speed of flow is very less. So in these cases, incompressible flow is used. So in figure you can see the hydraulic gear pump, and this is a what called air ventilation. You can see the air ventilation in houses. So these are the applications of incompressible flow. So this is the complete presentation of compressible and incompressible flow, and I think you guys can understand what is the main topic behind these flows. I guess this is all for today, and I hope you guys can understand these topics, and thank you for your precious time. And this is uh, this is for all from my side. Thank you.